Everybody, let's learn about exponential models. What the heck is an exponential model? Well, let's dive in with an example, and it should start to make a little bit more sense. Let's say we have a little bacterial colony with 15 cells of bacteria in a petri dish or on a piece of rotting food or whatever. But every hour, the bacterial colony is doubling in size. So after 1 hour, we've got 30 cells. After 2 hours, we've got 60 cells. After 3 hours, we've got that's right, 120. After 4 hours, we've got, that's right, 240. How many do we have after 10 hours? Pause the video, take a second, fill in the table, or see if you can come up with some other clever way of figuring that out. No, pause the video. Hit the pause button. There you go. All right, I'm going to assume you figured it out by now and you've resumed the video. You probably took your graphing calculator and you did 15 times 2 times 2 times 2 times 2. And you kept going over and over again doing, see if you can see the screen, times 2 times 2 times 2. And you may have eventually gotten to, what would that be? Something like 15,360. Great. There must be a better way. There must be a better way of doing that, particularly if I'm then going to answer the question of how many are there in 100 hours. Well, what could I do instead of multiplying by 2 over and over again? What mathematical operation is multiplication by the same number over and over again? Exponents. I could do an exponential function. I could raise 2 to a power. Instead, I've got to multiply 15 by 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times to get to this number out here. So why don't I just do 15 times 2 to the 10th? That should get me the answer. Note that is not 15 times 2, 30, raised to the 10th power. It's 15 doubled 10 times. 15 times 2 times 2 times 2 times 15 times 2 to the 10th. If I then want to answer this question of 100 hours, it's easy. Let's just make that 2 to 100th, which is, a really big number. There's a times 2 to the times 10 to the 31 in that number. There we go. Really big number. That's a lot of bacteria, probably taking over the world at that point. So that's kind of your little introduction to exponential models. Let's try another example here. Every year, my $20,000 car is only worth 90% of what it was worth the year before. Brand new, it's $20,000. 1 year old, 90% of $20,000 is 18. 2 years old, it's not $16,000. That's linear. A linear function, a drop of 2,000 per year. That's not what's happening. It isn't dropping by a constant amount. It's dropping by a constant percentage. So what's 90% of the 18,000? And yes, I'm going to use my calculator for this. I suggest you do as well. I got 16,200. Okay, year 3, what's 90% of that? Year 4, what's 90% of that? Year 5, what's 90% of that? To figure out what it's worth in 5 years. You have a second while I work it out. Pause the video if you need longer than that. And I got that my $20,000 car at 5 years old is worth $11,809.80. That's about what my car is worth. Makes sense. 5-year-old car. What would you pay for a 2015 Honda Civic? $11,000, $12,000 sounds about right. All right, how did we just do that? What did we just do to get that number? We took that 20,000 and we multiplied it by 90% or 0.9, 1, 2, 3, 4, 5 times. Again, we took an initial number In this case, it was 20,000. And we multiplied it by 0.9 over and over and over and over again, 5 times, or in the case of this, 30 times. How do you do that? How do you multiply by the same thing over and over again? You raise it to a power. And that gave me that $11,809.80. If I want to make that 30 years, easy peasy. Change that to 30. Now let's think about this. What would you pay for a 1990 Ford Explorer? I wouldn't pay much. A couple $100 maybe is about all I'd pay for that one. Let's see if this works. I got $847 for that. $847. Sure. $20,000 car, 30 years old. That might be worth under $1,000. That sounds about right for what that car would be worth. Moving on to another example. Radioactive element has a half-life. The way that we measure the life of radioactive elements is in what's called their half-life, which is the amount of time it takes for half of it to decay, which means to spit off radioactive particles and therefore turn into another different element once it spit off electrons or neutrons or protons and neutrons or whatever the case may be. And we measure the half-life for how long it takes for half of it to decay, and then half of it again, then half of it again, then half of it again. So let's say we have some element with a half-life of 1 hour, which is pretty darn short. I've got a 10-gram sample. Every hour, half of it decays. How much do I have left in 6 hours? Multiply by half, multiply by half. You're probably getting the idea now. 1.25, 0.625. Let's fill in the rest of that table. Take a second to fill that in. By 6 hours, I should have about, check your calculator, pause it if you need a second, resume when you're ready. I got 0.15625 grams. About 1/10 of a gram, or about 1%, 1.5% of what I had to begin with. Not a lot. 24, well, actually, back up. How did we do that? Again, we took that 10-gram sample. We multiplied it by a half over and over and over again. I'm going to use 0.5. Over and over and over again, times 0.5, times 0.5, times 0.5, times 0.5, times 0.5, times 0.5. What is the lazy way to multiply by the same thing over and over and over again? You raise it to an exponent. That would give me that final number. And again, 10 times 0.5 is 5. This is not 5 to the 6th. This is 10 times 0.5 times 0.5. The point to the 6th power only applies to the 0.5. PEMDAS. Please excuse exponents come before multiplication. 24 hours, let's just change that to a 24. There is not going to be much of this element left. 0.5 to the power 24 times 10. And yeah, I get 5.96 times 10 to the negative 7. Very hard to line this up. There we go. So that's 0.000000596 grams. Virtually none at that point. All right, what's the big takeaway? What the heck are we doing? How can we tie this all together in a way that is somewhat meaningful? Our big takeaway is if I start with A of something, A is 10 grams or $20,000 or whatever the case may be, and every X time, every year, every week, whatever, I multiply it by some number B. So I'm multiplying it by B over and over and over and over and over again. I'm doubling it over and over and over again, or I'm multiplying it by 1/2 or 0.9 over and over and over and over again. And I want to know how much I have at the end. I can just take that B, raise it to the power X, and multiply that times the A. And the reason I said it in that order is that's what the order of operations would force me to do. Exponents come before multiplication. A, that initial thing we have at the beginning, that's what we have when X is 0. What do you call Y if X is 0? What do you call the Y value that occurs when X is 0? You call it the Y-intercept. So A is really our Y-intercept in addition to our starting value. We have a funny name for B. If B is greater than not greater than 0, greater than 1. If b is greater than 1, that means y is growing. We're multiplying it by a number bigger than 1, which causes things to get bigger. Then we call b the growth factor. If we're doubling, b is 2. The growth factor is 2. If we're tripling, b is 3. The growth factor is 3. If b is less than 1, note, it will still be bigger than 0. It'll never be negative, because raising negative numbers to powers gets really weird really fast. Think about how a power of 1/2 is the same as a square root, and you can't square root a negative, and you start to see why that comes off the rails really quickly. So b will at least be positive. But if b is between 0 and 1, if it's a number like 1/2 or 0.9 or 0.2 or something like that, then every time we multiply the a times the b, the result gets smaller. Multiplying by fractions makes things smaller. If that's what's happening, then we refer to b as the decay factor. So b has a different name, growth factor or decay factor, based on whether this equation is getting bigger, growth, or smaller, decay. But it's the same number in the equation regardless. I'm going to stop this recording here, pick up a new recording from the next slide when we move on to some other examples and we talk about growth and decay rate, which is a much more real world and applicable concept than growth and decay factor, although it takes us one level removed from the mathematics.